When you work with complex numbers, you very quickly deal with an equation which is I squared equal to -1. And there is a lot of mystery around this. I is what we call the imaginary number. And when you put it to the square, so to say, then you get a negative value. The problem with this equation is that it is not a correct equation. It's not correct to write this. The problem does not come from the negative value. You would have the same problem for any complex number z that you try to identify to a number, which can be positive, 0, or negative. The reason why we do this and we are drawn to this kind of error is because of an abuse of notation from the way we have built complex numbers in the modern world, so to say, nowadays. What you have to do instead is always remember that complex numbers are, by definition, a pair of numbers, okay? You need two numbers. So this means that, for example, for I squared, what you have to do is provide what we call the real part, which is -1, and the imaginary part, which is 0. So this is the best representation you can have. It is abstract, but very clear. It is a pair. Now, in the modern notation, the way we do is that we write this as -1 plus I times 0. This is only an expression, which means that the plus sign that you see is not an addition on anything. It is just a convenient notation which works nicely with the operations that we do with numbers, with pairs of numbers. Okay, and we will see that. So you are not allowed to tell me, well, you know, I have I times 0, this is 0, and therefore I have -1 plus 0, which is -1. Okay, you cannot do this. Actually, you cannot do this when you come to the interpretation of your result. But now it is true, however, that if you take such an expression and if you multiply by complex numbers, other complex numbers, if you divide and do stuff like this, this term I times 0 has no role. It is as if it's not there, if you want, okay? So operationally, you can treat I squared as equal to -1. It gives you the same results, but you cannot conclude that this is a single number because you cannot equate a pair to a single number. So what I would like to do now in this tutorial is not to go through the history of complex numbers because you have a lot of resources here on YouTube and elsewhere, and they are, I think, sufficiently good, and you have Wikipedia pages and so on. And I will not neither go into a discussion on how you manipulate complex numbers, how you calculate the modulus, draw things on a complex plane, and so on, because this is also extensively used. Instead, I would like to do something which is really rare. You have to do some mathematics courses, maybe at the university, depends on which country you come from, so that we can build, starting from scratch, the algebra of pairs, not necessarily complex numbers, just pairs. And then as we impose laws and commutation rules and so on and so forth, we will see how we will be naturally led to complex numbers and how they are unique and why they behave in this way. And so we will see, for example, popping up the square of an I, which will be a sort of -1, okay? So I have here a pair, Z, which is defined by AB, where AB are numbers. I need an equality for this algebra because I have to equate things, right? So I will say that this equation holds true if A equal 2 and B equal 3, which means that I am identifying each row on its own. So all the terms in one row are identified to each other, okay? So this means also, as a consequence, that the pair AB is different from the pair BA. This is what we call an ordered pair, okay? And that is not to be confused with an ordered set. It's the pair itself which is ordered. Now I need to do operations on this set of pairs. And for that, I will have to define some sort of plus and a multiplication, right? So I will choose the simplest, which is the plus sign for the moment. And I will say that if I have the sum of two pairs, I will simply take every row and add all the terms in it. Okay, so this is why I obtain for this the result 2 plus 4 and 3 plus 5. Each row has its own sum. So you see here that I am defining the sum, the addition, I should say, of pairs from the addition of numbers. Okay, I'm using the same symbol, but this is more for convenience, but normally these are not the same operations. A consequence of this is that 0, 0, the pair 0, 0, becomes the neutral element for addition. You also have the commutativity of the sum, because numbers commute in between them. So given this definition, the system, the addition is also commutative. And finally, in the same way, I can always decompose any pair of the form AB as the sum of two terms. And in particular, I will write it as the pair A0 plus the pair 0B. And lastly, you have the rule of associativity, which is very important because it's very practical, which is essentially that you can have a sum of all pairs. You can add them in the order that you want. And this results again from the associativity that I have on numbers. Now, what about multiplication? Well, multiplication, I can, be very basic and just say, okay, I will do the same. I will take each row, all the elements of this row, I will just multiply them. So I have the pair 2 times 4 and 3 times 5. The problem with this kind of algebra is that my multiplication and my addition are keeping each row independent from the other. So I am effectively dealing with two numbers separate and they will never talk to each other. So this is essentially a useless algebra. I'm just duplicating. We can also then say, okay, so I'm going to do the cross product. Cross in the sense that I take, for example, the 2 and multiply it down by 5. And then I do the same for 3. I go up and multiply by 4. This will give a product which by definition does not commute. So I want an algebra which commutes. Okay, I could go into the direction of having non-commutativity, but I will not do this. I did not even try if this will give even an interesting algebra for this particular system of pairs, okay? But we know that we have quaternions, for example, they do not commute, and they do not, they have very interesting properties. So I need a definition of multiplication, which I have to find in a different way. And the way I will do it is essentially by going back to, let's say, to school when we were kids. Our parents and teachers taught us that first we learn how to add. So for example, 2 plus 2 plus 2 is 6. But then they tell you, miracle in some way, they tell you, well, now you have, I gave you 2 3 times. Okay, so you have this notion of grouping which comes. And so this is how you start counting and multiplying. So 3 times 2 is 6. So it's fantastic. Okay, and then you carry on like this, and you have your multiplication table. The problem with this, actually, it's not a problem. I'm going to use it, but I would like to say something important at this point, is that this idea that multiplication is a, how do you say, is a succession of addition. So it gives this impression that the multiplication is a sort of subspecies of addition, right? And that works with natural numbers, but it has its own limits, okay? You can imagine, for example, taking just numbers which are weird, like square root of 2, pi, irrational numbers, make a product between them and try to find a way such that this is the sum of numbers, okay? An intuitive way, an intuitive way. This is the point. So at some point, you need an abstraction to define the multiplication. And this makes sense because multiplication also represents a sort of scaling, okay? So when you have, for example, a rubber, this is a typical example that is given, that you stretch, and I tell you, make it twice as long. You cannot come and tell me, well, this is one rubber, and then I add another rubber, because I'm leaving you with only one rubber, and I'm asking you to stretch it, okay? So this idea of multiplication is actually cognitively embedded in us humans, so to say. So you need to give it a status on its own already at the level of real numbers, okay? This is not an issue with pairs of numbers or complex numbers in general. So now I can go ahead and say I have 3 identical pairs, so the result is 3 times this pair. That I can do, but I will not do it. Why? Because I have my 3 is a number, and I multiply it by a pair. So I'm going in the territory of having the product, which I'm still wanting to define, this is my goal, as an external product. And I will not do that, okay? I will rather keep it the conventional way in field theory, which is that I'm going to assume that the product is internal. So I am going to substitute this number 3, this grouping of 3 pairs, and I will say that this is the pair 3, 0 that I multiply by AB. This is how I am viewing the grouping of complex numbers, right? Now, the term which is on the left is just a bunch of additions. And that I know how to do because my addition is defined. So this will give me that the pair 3A, 3B is equal to 3, 0 times AB. Now I make the remark that my factor, which is a pair 3, 0, my 3 went up and down. It is multiplying not only A, but also B, okay? So I have a kind of a crosstalk which is happening between the rows of my pair, okay? So this is where I'm coupling the system, if you want. Now I can generalize this for any value of alpha different than 3, and this, by construction, is also commutative. There is also another property, is that I can now deduct the neutral element, and this is the pair 1, 0 for multiplication. Now, when I have a product like this, I need to say something else, because I know that any pair of the form AB, or even alpha, beta, I can divide it, split it as a sum of pairs. And if I do this, I want to be able to find the result, which is the pair alpha A, alpha B. And this, I can do it if I assume, since I'm constructing my algebra, I assume that the product that I am defining can distribute over the addition. Because in this case, if I distribute, as I would do with normal numbers, then I can recover the same result as you can see. So now what happens if I have any pair where I have a pair, let's say alpha beta, where beta is not necessarily 0? How am I going to define the product? Well, I will do in the same way as you do with real numbers, is that I am going to call for an abstraction. I am going to say, well, it will work in the same way. I want to be able to distribute because I know I can do it for beta equals 0. And normally when you impose a law, such as a law for distribution, you apply it for all the elements in the set. You're not going to bother with the special cases and so on. Okay, it's better, it's wise, because distribution is a really helpful concept. But at the same time, it starts to put some constraints on your algebra, and we will see this. And of course, I will also ask for commutativity. Now, the system that we have an addition, a multiplication. They are well defined, but the system is incomplete. I'm still not done, because if I take the pair 1, 0 and multiply by 1, 0, which is itself, I obtain 1, 0. This is normal because 1, 0 is the pair which represents the identity for multiplication. So in the same way, for the same argument, if I have 1, 0 times 0, 1, I obtain 0, 1. Okay, it's the identity. Now I can do also 0, 1 times 1, 0. And this, I can invoke the commutativity of the product, and it will give me exactly the result which I have just written before. So the most important thing here is that these three multiplications, I am able to know the result. The problem that I have is that the last term, 0, 1 times 0, 1, I still do not know what the value is. It's not possible with the current algebra to know the value. So what I'm going to say is, well, I write I equals 0, 1. This is a pair which I define. I give it a letter. And I am going to say that the square of it, I don't know it, but I know it is a pair. Okay? Because implicit in all my discussion so far is that the product and the addition, by the way, is a closed operation. So if I take a pair and multiply by another pair, I obtain a pair. But I still do not know what are the values of this pair. So this is why I say that this is a certain P and a certain Q, which I still need to fix. And we are going to fix it by putting an extra condition. Now, before doing that, I'm going to switch to the new notation, let's say the notations that we are all used to, because it's easier at the end of the day, to manipulate. And so the correspondence, you do it in this way. You first take a pair AB and you decompose it as the sum of two pairs. And then the last term, which is 0b, you write it as I times b0. Okay, you can check this on your own. It should be trivial, I hope, at this point. So this is still an exact equation. And also, I am using really the addition and the multiplication that we have defined on pairs. Now comes the magic, is that I say, well, I am going to correspond, I'm going to change notation. It's really, you are really looking for an expression here. And you say, well, the pair AB, I'm going to map it mentally to a certain A plus, with a round circle, IB. I put the round because I really want to insist, just for this slide, that this is not the addition of pairs. It's just symbolic, okay? This is an expression. It is telling you that when you say A plus IB, it's A plus IB. You cannot reduce it further because a pair is a pair, okay? But now I have freedom, a certain set of freedom on this symbol. I can play with it. The only condition, restriction, I should say, that I have is that I must respect multiplication and addition of pairs as I have defined them. Otherwise, I'm doing something random, okay? So I'm going to take the first liberty, which is super important actually, and that is I'm going to say I can commute with this plus. This plus commutes, visually commutes, okay? So I can write A plus IB equal IB plus A. And these two map to the same, very same pair. Fundamental, okay? So why I take this liberty? Because in life, when you do math or physics, you write equations and you write horizontally, okay? So you will have a bunch of complex numbers that you will need to add and subtract and so on. And so you want to group them. So you want to have this liberty. And that's okay. You can do it insofar you know how to map them to exactly the same pair. And now, for the mapping for numbers, you say that a number A, you can map it to A plus I0. And that represents the pair A0. And the same for IB. You see how I keep I and B always together? This maps to 0 plus IB, which is I times the pair B0. This is the correspondence, if you want. But now there is another thing which I have to invent, so to say, is when I deal with a product like this, I know that AB, I can decompose it as a sum of two pairs. So how am I going to deal with that? Well, actually, you are just going to assume that when you do the multiplication and you have this rounded plus, in the middle, you just say that you can distribute, okay? Because if you do accept this distribution, you will find exactly the same result, which is alpha A plus I alpha B, which then maps to the pair alpha A, alpha B. And that's it, So this is why now this circled plus, you can just forget about it and put a plus, okay? But it's not the addition on pairs, full stop. This is the usual notation. And now I come back to our problem initially, which was to determine this famous I squared. I know that it's P plus IQ, and I still don't know what the value is. So how can I fix this? And actually what is missing so far is that I didn't ask for division. So I'm going to allow for division in my algebra. And then we will see what happens if you do not allow this, okay? I'm going to accept division. Let's go for that. So this means that if I have any pair, a plus ib, then if I multiply it by another pair, I can tune this other pair, alpha plus I beta, such that the product is equal to the identity of the multiplication. Okay? So said differently, for any complex number, AB, I can find a pair alpha beta such that the product is equal to 1 plus I0. And this I can do it as far as A and B cannot be 0 at the same time. One of them can be 0, but not the other. They cannot be 0 at the same time. Okay? So now, how do we do that? Well, actually, you just develop. You know the distribution rule, and you have two sums. So you go ahead, but you have to be careful that when you do this, you should not equate I squared to minus 1. You leave it as I squared, which you can see here. And then you replace I squared by your unknowns, I should say, which are P plus IQ. And then you rearrange the terms. And finally, you equate each term. You know how to deal with the equality of pairs. So you go ahead and you obtain two equations which are coupled. So the goal in these two last equations is that now I am looking for alpha beta. Okay? I want alpha, I want beta, and I want them to have finite values. I want them to make sense, knowing that I have all the liberty I want on A and B, except that A and B cannot be 0 at the same time. And I have a liberty on P and Q such that this always works. Okay? So what I'm going to do is, well, I have to isolate alpha and beta. So I hope you know how to do that. But this is, let's say for beta, what you would do is you would multiply by minus b the first equation and plus a the second equation. And then you add the two equations such that you have an equation only for b. There is no alpha anymore. And this is the equation you would have. And you would have also another equation for alpha, which I will not write, but which will have the exact same term which is in between square brackets. So now comes my condition. I want beta to have a sense. So for this reason, the term in square brackets cannot be 0. Okay? So how are we going to have this term not 0? It's not obvious because I can take any value for A and B, almost. So the better way to do is to try to isolate as much as possible P and Q, because these are the numbers you want to play with, okay? So for that, you can recognize that the first term actually of the square bracket is actually can be written as a square, but an incomplete square. And you complete it by subtracting the term Q squared divided by 4 times B squared, okay? So you can check this if it's not obvious for you calmly. I think it should be okay. And the thing is, now I have the sum of two squares. So that's fantastic because I know that these are positive numbers. But I have also P plus Q squared divided by 4, which pops up. So if I set P plus Q squared divided by 4 as being negative, then given that I have a minus sign already, then I will obtain for this equation something which is always positive. And it cannot be 0. It cannot be strictly 0. Why? Because if B is 0, you can check that then this equation, this term reduces to A squared. And A squared cannot be 0 because A cannot be 0 because B is already 0. Okay, and you cannot have both of them at the same time being equal to 0. So this condition is sufficient, and that's fantastic actually. Regardless of the values of A and B, as far as A and B are not equal to 0, I have for any pair I squared for which the square is of the form P plus IQ, if P plus Q squared divided by 4 is negative, then I have a system where I can always find an inverse except for 0, 0. Okay? So this is, for example, the case that we know p equal -1, q equals 0. This works, okay? Because this will give you I squared equal -1 plus I times 0. But it's not the only case. So what happens, for example, if I have p equal -5 and q equal 2? This will give me I squared equal -5 plus 2i. Wow. And you have an infinity of solutions like this. So is this a different algebra? It's actually the same algebra. You can map it. So I will just sketch quite quickly how you can do this. You start from I squared equal p plus iq. And this equation, regardless of the values of p and q, you can write it in this way. You can check, it should be fairly easy, okay? You just create a square by shifting. So now the last term, the term on the right-hand side, p plus q squared by 4 divided by 4, is the term that we were discussing. I know that if this is strictly negative, then I have a division system. So I'm going to say that this term is equal to minus k squared, where k cannot be 0. And for that, this means that I can define a j in this way. I'm not going to spell it out, for which the square of j is equal to -1. And now I can invert this to get an equation for I. And this means that now for each time that I write a complex number as a plus ib, I can always write it as an equation where I have a number and j times another number. So this is a mapping because it's bilinear, if you prefer, in a nutshell, okay? So even if I choose an I for which the square is bizarre, I can always map it back to a number where I have a certain j for which the j squared is equal to -1. So this is essentially an equivalent algebra, okay? And the choice I squared equal -1 plus I0 is simply the simplest because it has a 0 imaginary part, okay? It's a convenience, if you prefer. Now, that's it for complex numbers, but I will just briefly mention what happens if this equation, this inequality is not satisfied. Well, this is the case, for example, for p plus q squared divided by 4 equal to 0. In this case, you can map to a sort of complex number for which the square is 0. And these are what we call dual numbers. They are, if you heard about Grassmann variables, they do exist. We use them in particle physics. And they are the simplest form of Grassmann variables. So they have a certain utility. They are just not as popular as complex numbers. And these numbers, they do not accept a division. You cannot always divide, okay? That's the difference with respect to complex numbers. And then you have the last case, which is p plus q squared divided by 4 being strictly positive. And this can be mapped to a sort of an I for which the square is +1. These are what we call the split complex numbers. And they have a certain analogy. They behave a bit like a Lorentz transform in one dimension. Because as you can see, the term beta, which I just wrote it for you to recall it, you have a squared minus b squared. And you can see that this can be 0, by the way. So it's not a division system. But more importantly, so to say, you recognize something which behaves like the Minkowski metric in one dimension for space, okay? So I personally never used split complex numbers because if I work with Lorentz transform, I typically do it in 3 dimensions for the space. So that's all for complex numbers. Their beauty is that with respect to the others is that you have an inverse. And this is really what brings you to the conclusion, if you want, that you must have this I squared, which is equal to -1. But don't forget the plus I0, okay? So that's it. Thank you very much. And if you like this stuff, feel free to comment, good or bad. Just don't insult. Be cool. Like, this will help. Subscribe if you really believe in it. And go ahead. Thank you very much.